from this first slide, I have changed the title a little bit. As you said, I will speak about modeling, but I think I want to focus more on what we have been working with mostly with and where I have my largest experience. So I'll talk a little bit about high resolution modeling and some application, how we use these models, which I think is important for the physical twins, and also some of the challenges we face when we're working with this. As Bente mentioned, we're working with a model framework called SINMOD. This is an in-house developed model code, and it is a coupled physical and chemical and biological model system. It's developed here at the SINTEF Ocean in Trondheim, and in recent years we also have the people from the university here participating and developing the system. So this is a regional model system, which we start usually at 20 kilometers as model domains, and then we go down to really high resolution models, down to 32 meters. I will get back to that. So this is a model system that we run a lot in the high-class mode, where we're doing different studies in different projects, but we also have applied it in an operational, we can run it in an operational way to provide forecasts that we have done in several projects. So for my background, I'm doing modeling, and my background is mostly in coupled biological and physical modeling. But if we start with a simple model framework and focus on the physics, we have a hydrodynamic module that is based on the primitive equations, giving you the current, temperature, and salinity. And we also have an ice model going online. With that, we have a, So this is the hydrodynamic model. But what I think is best special about SINMOD that it's been developed as a coupled biological and physical model system since the 1980s. So we also usually always working also on the biology and other modules in addition to the hydrodynamic model. So the ecological model system includes typically 14 to 16 states. We have states for nutrients, phytoplankton, zooplankton. We also have included here just simplified version, but it's 14 states, and we have also microbial processes in there, and also a module for benthic and deciders and so on. We also have modules here within the system for the carbon chemistry and also oxygen. And then we have some more specialized models for different species, like the blue mussel, seaweed, or more specialized towards aquaculture. We also have models for migrating coastmods for rivers, and we also have our population model for sea life. And I mentioned this, and I will just show you an application of this and how this how this actually works. So then, in this case, we just run the hydrodynamics and this sea life model and this salmon coastmod migrating model. We start here. You can see the west coast of Norway, and you can see there's a concentration here. And this concentration is sea lice as individuals per square meter. So what we have done here is actually release the sea lice from all the fish farms according to accounts of female sea lice on the farm. And then we calculate the development of this sea lice, because the sea lice has a pelletary phase. So we calculate, so we simulate the development of the larvae from their larvae until they are infectious coprolites. And that's when they can stay on a smolt and also affect the wild smolt. So this shows you just the releases with the fish farms that are close to the coast, and you can see it's out to the coast with the brackish water outflows, and then it goes into the coastal current. A second step here is to model the migration of the postmods. So the postmods are migrating from the different rivers along the Norwegian coast. So this is an example of our modeling. This is one smolt going out in the fjord, and you can see it follows the currents and then it moves out of the fjord. It takes a bit of time, but you can see it's blue colors and red colors, and red colors is where it actually meets sea lice. So this is where it is exposed to sea lice pressure. And the end goal in this actually system is to have an estimate of number of sea lice on the smolt in the end. Because what we want to know is how the fish farms in Norway can affect the mortality of the post-smolt on wild salmon as a result of the release of sea lice from the fish farm. So this was one application. Another application we work with is the location of fish farms. One of the new things is to have these fish farms in open water, offshore fish farming. They're talking about concepts that are quite large. Here's the one concept called smart fish farms. You can see the size of it. So work here has been analyzing quite large data sets, and we also produced a large data set of SINMOD data, 10 years of data where we analyzed different environmental conditions to find good locations for this farm. Just an example, this is a mean value of the temperature that is interesting for them to find a good location. But again, since sea lice is important in Norway to see the effect of that, we also want to find locations so that if there is an outbreak of sea lice in this fish farm, the sea lice should not reach the existing fish farms along the Norwegian coast. And the same, we are doing the modeling the other way. We look at how diseases or sea lice can be released along the coast and how then they can reach potential locations of offshore fish farms. This is another example. But a little bit to the challenges. So here you can see a picture of how this looks outside the coast of mid-Norway. Here you can see a fish farm, and you can see it's quite close to land, and there's another fish farm over further out. And you can see that this is a quite complex environment, and this is something we have to work with if we want to produce some realistic environmental conditions in ocean models for these fish farms. So to give you an example, we have done this simulations with 32 meter resolution. So you can see here is the current speed, blue is low currents and red is high currents. And you can see the tides going back and forth. All these names are different fish farms in this area. It's again outside in Norway. But what you can see is how this local topography is affecting the currents and why we have to go down to really high resolution to try to resolve it, which we need for some specific problems related to agriculture. Going to another challenges, our challenge is this is actually from a really nice, we had some really nice days last week. And when we have nice days, we also have nice satellite images. So this is from Sentinel-3. So this is estimate of coastal A. You can see again Southern Shore. This is the coast of Norway. And then you can see the bloom outside here. And one of the reasons I like to see is that they are very dynamic, very beautiful, but they're also very complex. And it also represents a challenge when we are trying to model this with a combined physical biological modeling. So I'll just guide you through some examples. This is an example of zooplankton. This is something we produced with a model. So this is a snapshot of biomass of zooplankton outside the in the Norwegian Sea, and you can see you get some structures. But if you zoom in and we play with different resolution, we see that this is 4 kilometers, and if we go down to the 20 kilometers, we don't see any processes at all. But if we go at higher resolution, we can see that the biomass distribution is getting more complex, and the eddies or the mesoscale dynamics are looking more realistic. But the problem is that if we even go to even higher resolution, we can have a picture like this. You can see this is within the square outside Lofoten in Norway, and you can see really, really detailed and large patterns in the distribution of the zooplankton. This is also something we work in a project, because zooplankton is also can be a harvestable resource, and we will not want to know the amount. We want to know where we should go fishing for it, and then we also want to know how this is distributed. But this is a model result, and we need to know a bit more. Is this a realistic patterns? Is the physical processes correctly represented? And we also have to look into the biological processes. And then a question that we have raised: what is the correct level of patterns? Is this a model artifact, or is this something that's actually If I have time, I just had another example showing this with other problems or actually opportunities. This is just showing, we're looking into the potential of growing seaweed in Norway. It's done already, but we are also looking at where it can be grown. So this is just showing a conservation potential that is calculated from the model system. So it tries to guide it where the greatest potential is. And you can see there's great potential out in the deeper sea where you have more nutrients available, but you can also see there's a high variability closer to the coast. We also look at seaweed as a potential carbon capture way. So this is just showing that we can also calculate how this carbon capture can be done with seaweed and how much carbon they can capture to calculate the CO2 uptake in seaweed and see a similar map of that. That is of course related to the potential of growth. Yeah, I want to mention the last slide here, something about assimilation observations, because that's also relevant. We're working with NTNU that is working on the observational pyramid, where you have the satellites covering a large area, and then you go to the drones, surface vehicles, AUVs, and so on. And these are definitely different levels of observations that you can utilize and use in data assimilation of the model system. But this is quite complex. There's different levels, the different types of data that is simulated in different way in the physics and biology of the SINMOD model framework. And we also have the different, again, scales. How we're going to simulate this into the high resolution models or the quarter resolution models and what effects that have. This is something of the topics that you're working on, especially at NTNU. So yeah,